Hi, I'm Edakwa, and I'm working on my new game Rabanaz, a chip-based deck builder. Tinker with your chips, slot in modification tubes, and reshape the scoring to craft your ideal strategy. On this channel, I'll ruffle my programming feathers and talk about some of the technical aspects of Rabanaz. Alright, let's take a step inside the casino and see what the Ravens are up to. Hi, Edakwa here. Today, I want to look at the part of the game of Rabanaz which is a little bit related to the story, and that's with these little characters here. These are little ravens in the game. They come up when you have these bad tubes. The bad tubes are there to hinder you. And when I created this, I thought, although we did this nice display for the rest, we didn't do pixel graphics. I thought it would be nice to have sort of for the steampunk effect to have little pixelated graphics in the game. And so I had this idea to put these here, and we found this excellent artist to do these little pixel graphics. And then for the CRT effect, I thought I'd round it off. And so today I want to look at how I do this pseudo CRT effect in Unity with the shader graph. Yeah, so let's take a look at this. So this looks pixelated. I'm going to stop this one. I'm going to go over a special scene we have for testing these because it's a little bit easier to see what's happening there. So I have this scene. You can see there's two of them here. I have the one in the ring and then just one standalone. The standalone one is a different color. And that has an effect in the game too. You can change the color. Okay. So if you look at these things, they're at the basic, they're 32 by 32 graphics. I can show you what one of them looks like. For example, this one here I think is bad clingy. And you can see down here in the preview, it's really hard to see in Unity because it doesn't really zoom in the preview, but you can see it's really tiny. It's a 32 by 32 graphic, pixel graphic. And that's what it looks like here. One thing you'll note when doing this in Unity is that if I don't move the mouse, there's no animation because it doesn't actually redraw the scene if it does nothing to redraw. While it's live, obviously, this is a time-based effect. This effect has several aspects to it. If I jump over to what's known as the shader graph in Unity, this is the thing that puts together the little display of graphics. Overall, this is not a complex shader graph. If you look at some of the other things people are doing with graphics, the shader graphs get really extensive and have multiple groups. This is a relatively straightforward one with a few moving parts. It does have a source file attached with it too. I'll open this in the other one too. Maybe zoom in a bit. And so this is the same one on both sides. I can open on both sides here. Get back to Unity. And I want to show off little bits of it so we understand what's doing it. Let's take part one. The actual scan lines. So, well, actually take a look at let's look at the scan lines first. The scan lines, if you see there's multiple effects here, there's actually little scan lines. And I say it's pseudo CRT because this isn't really what a CRT display does, but it makes a nice effect by showing the little black bits in between the lines. And this is done with this little bit down here, this remapping down here. It has a scanline custom function, and it does this scanlining function. And if you want to see what it looks without it, I can sort of just remap this and take this output from here and put it directly over in the base color. And you can see what it looks like without the scan lines. So this is what it looks like. It's still kind of fun, but it's missing something. And that's kind of why I added the scan lines. If they weren't there, you might never notice it, but it's just kind of fun. And then we put this back and we get them back in place. As I said, it's a pseudo effect because it's not real. In this first part of the video, I'm just going to show you how to turn on off I'm just going to turn on and off the bits to show what I was like. Afterwards, I'm going to go through some of the code and more details on how this actually works. If you're interested in that, for the first part, I'm just going to keep showing how the little bits are. The next bit is this noise function up at the top here. And that is, if you watch, it looks like it's just a fuzzy display. Noise is going on and off, and this is like old TVs did this. They were just fuzzy. There's a few things I'm going to draw your attention to is that the fuzziness isn't over the whole screen. The fuzziness is also pixelated. And I think that creates a better effect than just noise all over. The fuzziness is also, it has a frame rate. The frame rate is like 10 frames per second. You don't really see in the Unity editor. And the reason I did that, because if I adapted the noise to like your actual frame rate, if it's 60 plus hertz on your monitor, you just wouldn't see it. It would just be like a constant sort of brown. So I limited the framework to 10 so you can actually see the noise to it. And that's the part of the shader graph up here. I am using the Unity gradient noise, which is a Perlin noise function, I believe, or something similar to. Then I remap it, do a few things, add the noise, and it comes over here. And if you want to see it without the noise, we can go and take this and put it over here, I believe. And now you get it without the noise. So this is how it looks without the noise. Again, it's nice, it's not bad, but you can see how it misses something a little bit without that. So let's go and put that noise back on. Now the other one, which is kind of the subtle effect, oops, I forgot to press save, is I wanted to have this round display. If you've seen an old CRT TV, they have more of the sort of rectangular shape, but this is more of a round shape. And I actually did the calculation to get the proper round shape, and it just doesn't look good. So this is actually fake. It's slightly rounded. If you look at the little lines, it's slightly rounded, but it doesn't really conform to this display. I just kind of did that just so you know, it looks rounded. It's better to see over here, it fades in the distance. Like in this graphic here, it just kind of feels like the ring's fading up, but you can actually see the fading over here. Now, this one is really hard to turn off. I can't really demonstrate it without this effect because of the fact it's fundamental to the way this is all connected, and I can't remember how many lines I have to disable here to disable the effect. But I think if I go to the code, I might be able to find what effect did that again. So the screen distort is right here. So it's all this stuff here is doing the screen distortion. I think it's to project a curve here. Yes, that kind of removes the distortion, but it removes a lot of the distortion, but not so much. It's a lot flatter, it's harder to see. The distortion isn't honestly that high because if you put it too high, it makes a really weird effect. Okay, and it breaks. So just trust me on this one. It's really hard to show with it off. There's a subtlety here, and I can turn it on and off. But it's really subtle, and if you go for the realistic display, it actually starts to break. Unfortunately, I can't really display it without it. Another effect that's a little bit hard to see, and I explained it to my partner when she was playing the game. I think it's the Vampire Survivors Crawlers. It's another game that has pixel graphics, but they aren't pixel graphics because if you look at the game, it's low resolution sources, but the pixels on that game are perfectly anti-aliased to a 4K or whatever display you have. And I had the same effect here, and this is a bit hard to explain because if you look at this thing, hey, it just looks like pixels, but if you think about how this maps to the actual display, this isn't how it works. These are not really pixels. If you zoom in, you can actually see that I have some shading around them. So this image actually has to map to real pixels in the display, and this is not a one-to-one mapping. As you see, I scroll in and out, I still have this pixelation here, this sort of virtual pixelation. And so what's actually happening when displaying this graphic is that we're also not using the typical graphics format where you stretch the image, because then that would create a blurry motion. We're doing a special sampling where we sample individual pixels, but then we have a roll on and off so that's a smooth gradient. Because if you don't have the smooth gradient, then you would have pixelated pixels, if that makes any sense. Now, it's an interesting effect if you've ever worked with SDF, so sign distance fields before. It is the same effect, but just on pixels. And if you ever see other pixel games, like I say, the crawlers, vampire crawlers, just watch for when you have pixel graphics that actually have really smooth borders on the pixels. It's not a simple effect. And in my shader graph, I did this. This is it again. A lot of the stuff in the shader graph is not something Unity natively supports. They just have custom functions. But you can see it right here. I combined it two together. There's two things here. So in Unity, in a normal graphics function, this gradient represents the position in the picture and where you're going to sample from the graphic. And so the first thing I do in this path is I make this special function, the screen distortion function and this pixelization function, where you can see this is actually a pixelated thing, a pixelated sort of mapping now. It's still a gradient, but the pixels are already here and they're already mapped to the screen. And that's how it's applied to all these other ones. You can see that pixels already at these various stages in it. And here you can also see it too. There's shading on the sides to be gradient pixels. Now, if the pixels were perfectly aligned with the screen, I may not have to do the shading and get away with it, but they're not. And also because of the scanline effect, because these are slightly bent to the display, and this is, let's see, if you see it slightly bent, you can see the guidelines in Unity, maybe. You can see there's a white guideline, and you can see it's slightly bent. This is the scanline effect, yet the pixels actually still maintain their pixeliness relative to the virtual display. And that's what I wanted to show. So we have several of these. We have the color effect too. Like this is just a random multiplier. Let me just show you these things to run inside so you can see the final effect together and a couple of them side by side. And so these are just simple animation. The animations themselves are 4 or 5 or sometimes 6 frame animations, 32 by 32 pixels. Again, we have an artist doing some lovely work on these, very expressionate for little things. And these are put in the game on the main screen. They appear in the shop too for the vendors. I did say there was another color effect here. So if I go to the color here, in particular this one over here, there's a color on these. These were the two colors I'm debating between. This one looks nice too, but the green felt like more the classic effect. But you can basically choose whatever color you want and you can see it. Now this red effect I thought was interesting. The blue one maybe. And so the red effect was interesting. I thought, well, we can work with this. Because we have limited palette graphics, we can actually do something with this color effect as well. Let me go show you that. If I go over to another scene, I go back to the basic round. Let's just not save that. And I run this. I have it set up to play the guillotine guy, the guillotine raven. He chops up chips when you drop them. That blue flash doesn't exist in the final game. It's a Unity issue when playing here. And so he has these idle animations. First of all, you can see idle animations come up. And if I activate him, so every second chip or so, you'll see him activate. Watch. And that's, you can see I switched it to red. So I put an animation there switching it to red. And that's one of the advantages of the limited palette and having the shaders, that we can control the actual CRT tube color itself. And so when he's angry and get activated, or if he does something, I can make it red. I haven't found a use for another color yet. I may or may not. We'll see. There's not a lot of things that can happen with it. All right, that was it for the general introduction to these little shader guys, these little ravens, I should say. I can go through a bit more of the details in the second part of this show. If you're interested, I'll just go deeper into the shader graph, but this is the general idea of how it works. We have these ravens in the game, and they have these little animations. These are cute little pixelated animations. I had this idea of having this little steampunk sort of CRT display to give it a retro sort of effect. So the rest of the game is in sort of the hand-painted 4K graphics resolution, but the actual characters here are like 32 by 32 pixels, really tiny, and I think it's thematically fits and gave us a way to introduce some animated characters. If you notice, he sometimes thinks, and that's just an idle animation. So we have a few idle animations. If we have time, we'll get more, but mostly they're static and they have idle. If you notice when you come into the screen, they have an entry and an exit animation. It's really difficult to show in the Unity Editor stealth because there's so much stuttering on screen load, but they are there. And he also has an activation effect. So I dropped one chip, every 2 chips or so, he chops them in half. And so the chip, the six here will become split into 2 3s. And you can watch when I drop one that he's actually going to do a little chopping animation. And he turns to red at the time we do it. These animations are all limited palette. We thought that fit with the theme well. So there's a little bit of color here. So again, completely fake CRT. Also the fact we have true black and white and still a tube color. It's fake, but it produces this nice effect with a few highlights. And again, we can change the tube color if we activate him. All right, so now I'm going to look at a little bit how this effect works and the various parts of it and how we can turn it on and off, just to explore that. Okay, so we took a general look at the overview of how I did these graphics, in particular the shader effect. And if you are a graphics programmer in Unity, you probably recognize the shader graph display. It's kind of hard. I find it kind of hard to work with, but you're constantly scrolling around. You can make groups, but it's really hard to make sense of this, I find. But this is where all the parts are. I want to look a little bit more in detail at these parts and what I'm actually connecting here and how this gets done. This is using a lot of sort of Unity things. Like, this is why I use the shader graph and not pure code. I honestly wish I could use pure code at times, but some of these things like the local UV, I don't have a function in the code to call this with, and it's really helpful. So this sets up my basic UV coordinates for the graphics, and then you have the sample texturing and stuff. So some of these things are really helpful. Like the Perlin noise is also a standard node thing, standard node, and time is a node. So we have these standard nodes that are really convenient to do in this one. What's also kind of helpful in this display is having these sort of stepwise previews. A lot of times they don't look like much, but they're really useful for debugging. As I showed in the main display here, like right here, you can see the pixelization here. And let's just start there looking at it. Is that when I said the main display was pixelated, this decides what the pixelation is. And we said it's 32 by 32, so this has to be 32 by 32. If I go and look at the code here, I have this set up somewhere. Where's my 32? There it is. Screen is stored at 32. Sprite size is 32. If you change it to 64, well, okay, I have to zoom in more before you can see the graphics, but this changes it, and that's the, let's make it half the size. And now it's 16 pixels. So it works to create this 16 pixels, but as you can see, my preview gets very wrong because everything else is set to the 32 by 32 pixels. And I will say this shader graph is not generic right now. I've hard-coded a few places that are 32 by 32, just because it's the only size I have in my game right now. Obviously, if you want to make this generic, you'd actually have to have a variable for the shader graph that says, what is your sprite size? And I never did that because I don't need that. And so the 32 comes up in a few places. Also up here in the noise function, this also has a size. And before I mention the noise is that if you look at the noise, you can see the noise within the scan line. And I wanted the noise to be pixelated, but if you make it the same pixel look good, so I just doubled the sprite size. But if I go and set this back to the actual size, it also produces noise. The noise isn't perfectly aligned with the lines, but nobody knows that. It looks good, but I just found the doubled noise looks better. And if you want to, if you really want to see what it would look like without the scaling, you don't actually see it. It just kind of creates a texture. There is a noise there. I wonder if I can zoom in enough that you can see it. You can see the noise still, but it just kind of creates a texture. So that's not much fun. So I put it at double the size of the pixels, and that's what this function here is doing here. Let's look at this graph. Like, this is a good one, and I'll come back to the scanline and look at this. So I said this is a Perlin noise function. Now, importantly about that, those are gradient-based functions. They have a continual smooth curve, but this obviously is not a continual smooth curve because you don't want that. But having the Perlin noise their function, it simulates randomness because there's some guarantees about where this is. A good thing about CRTs too is that you want the gradients because otherwise you might have random walk type clusters, and that doesn't feel very good, even if it may be legitimate. It's just the Perlin noise kind of guarantees you don't get that. And so what I've done is I have this stepping remap function for the UV, and this is where this function comes in. So you have, what do they call it? If you look at here, the step remap function. So about half the nodes in this display are just custom function. It takes the UV in and the time in, and it produces that stepwise gradient. That's the function right here. There's an FPS on this too. If you didn't notice, the noise has a very particular frame rate. It's hard to tell in Unity because this doesn't refresh all the time, but the frame rate is 10 frames per second. Since our graphics actually have these characters work at like 4 frames per second, it makes it look noisy without just being too much noise. Again, as I said in the main part of this broadcast, if I don't bind that at 60 plus frames per second, you don't see anything. It's just a continuous distortion. So it's not much fun. So I have the frame rate. And this part here is the most critical part, the time times the FPS. This gives a stepwise function. So this is not a continuous wise function. This makes a stepping function at the frame rate. So you don't get a smooth motion. Otherwise, the graphic here would just slowly scroll, which is what you don't want. And this hash 22, so this is interesting. This function you can find online, variants of hash, there's all sorts of hashing functions. The purpose of this is to create a pseudo-random variable, because again, Perlin noise is a continuous gradient of noise. If you step in one direction, it would simply create a smooth function. I actually want to see if this actually works. If I just put the frame in here, do we get that continuous smooth function? We get nothing. So I think I have to get that more. Oh, because I need the offset. I need frame divided by 10. Let's see what happens. Uh-oh, I've forgotten how my function works. I think I got something wrong here. Let's just cut that part out. If we remember. So this is all the setup here. I forgot exactly how I made this work. I gotta be honest there. But you have this stepping. It creates a smooth stepping, and this hash is effectively saying jump to random locations within the Perlin noise. It's not completely random, but it's good enough for the visual. And then the UV out is doing two things. It's doing the pixelization of it, as well as scaling it per, like the pixelization for the scale I said. That's the main thing, the UV plus the offset. So the offset is how much offset it has, and then does that. And this creates this noise function output. And then the remap is simply, we don't want to go to black. We want to go to white. You want to have just ranges, otherwise it gets very dark. This one's an easy one to adjust. If I put 0 here, you'll see it looks, wait, I forgot to save again. It looks pretty off on that, guys. And in this case, you could really notice the pixels don't fully line up with the scan lines because I'm not putting them through the same distortion effect. Okay, let's put that back to 0.7. Okay, so let's go back to that distortion effect then. This distortion effect, you can see it's also a screen distort function. It's one function. It takes in the true UV coordinates and outputs pixel-based coordinates and an alpha channel and a line height. Those are interesting parts of this here. So let's go look at that function. As I say, the biggest parts of the shader graph, even though there's a lot of nodes here, the most important parts are custom function nodes, and this is probably the biggest one to do scan lines. So if I go look at the screen distort function, screen distort float, that's just what they called. And this thing does a whole bunch of things at once. And that's where it can sometimes be a bit hard to understand. And I optimized it a little bit, making it harder to understand what it's doing. Important bit is this bit here. This is doing the scan line, the scan line curving to make it look like it's part of the display. As in the main video, I used to remember how to get this to do different scan lines, but now I've kind of forgotten, because projected curve is supposed to be, if I put it to 1, it's supposed to be flat. Okay, it kind of is flat, but the issue is that it still has the shading, and that's this. Okay, so it's still flat. This is the weird thing, is that, so I was correct. This is actually flat, but the problem is because I'm still doing the shading, it still looks somewhat round. And so if we take off the shading as well, well, that's apparently not just the shading. I don't know why it's doing that. Why is that not? Do I have to go to the stage graph first? I think I have something else doing shading too. I might have another one. But okay, but at least it's not round. And if I make it too round, I forgot what happens. It gets too round. This is, okay, I think this is the problem with this, is where it's really, really hard to see, is that when you have a very round display, what this theta is actually the curvature of the display. And as I increase the curvature, it's actually, just imagine like a round little fishbowl or a sphere, and you're projecting an image on it. As I increase the curvature, it's actually a smaller and smaller portion of the front because the rest of it's out of display. And I think that's what makes it hard to sort of play around with this value here. But here's another one I put 2, and you can see it's a different curvature. And this one, so it's more curved, but you can see what I meant now is that I find it's too curved in a way. It's like, it's not really, it's more correct, but it just doesn't look as nice as the original 1.5. Let's see if I can get it to work at a slightly higher one where it doesn't just become too pixelated. Okay, here's a good, 3 is a good one here. You can see how it's very, very much sort of very round now. Honestly, for this size of image we have in the screen, this display, if this were truly like a capsule-based display in reality, it would look even more than this, but obviously it distorts the graphics too much that I just didn't want that, even if this is realistic. So let's put it back to the 1.5. And again, here, I also said the sprite size is here too. But if you mismatch it again, it just gets confused because the rest of the thing is matched. So it does do pixels, but because the rest of the sampling is based on 32 by 32, it just get kind of confused. So this is the important part. Now, I mentioned also in the main program that one of the critical things here, I don't know why I can't scroll around anymore, okay, is that you have clean pixels regardless of what the screen size or screen resolution is. Like these virtual pixels actually look like pixels. And this has a lot to do with this right here. If you've done any work with graphics, fonts, or sign distance fields, you'll probably recognize this function here, this plateau type function. I think, is it actually in, did I write this one or was it part of Unity? I don't remember. Oh yeah, plateau 01. So what I'm doing with the plateau is that you'll see the value right here is it says how much of the pixel am I dedicating to the gradient to switch to the next pixel. And this one here, I don't know how much this has to line up. The ramping has to line up. I don't know why. I just stuck the 0.5 in all of them. And what this is doing is it's creating that pixel fall off effect. So it's actually anti-aliased. I can zoom in a lot here and you'll see that there's actually a gradient here. This ensures that when this monitor, the scan line is rounded, that even at the rounding edge, you can see the gradient is rounding. As I said, this is a sign distance field for a pixel. It sounds really weird. And as I mentioned, the game Vampire Survivors Crawlers, the pixelated one that has like the perfectly anti-aliased pixels, somewhere in their shader graph, they have a very similar function because it's very standard sign distances. You dedicate a part, the virtual pixel to be the shading towards the anti-aliasing towards the next pixel, and you do a gradient between them. And at the pixelized level, you don't notice it, but it looks really clean. But if you zoom in, you can, again, very clearly see that they have a blurry transition. I'm just actually wondering now if I change this, if I say what did I say before, 0.5? Or 0.1 now. I can't remember which value I think she's. I think it's all of them here. Okay, so that's too much. I think my comment might be wrong. Or maybe my comment's right and I have an error in the code because that still looks pixelated. And the gradient's still pretty small. You know, I might actually have an error. Maybe that was meant to be 0.5. I'm gonna double check that later, but this still looks pixelated. Even as you zoom in, it stays pixelated, which is the intended purpose. So maybe my comment was right and my code was wrong, that this should be 0.5. Okay, interesting. These ones I don't think should stay the same because the edge, this is relative to the edge. And so it's x divided by the edge. So it's just a relative, it's like your typical curve. It's gonna go linear up, plateau, linear down to get the pixel transition between that and the next edge. If I do 0, it's probably gonna complain because I have a division by 0. So let's put a really, really small one. Okay. All right, you can start seeing the problem now that right here, I don't know if you'll see this in the video, is that now it's actually being clipped too much to the pixels of my screen and it's starting to look choppy. It's gonna be tough on, say if we're watching this in YouTube or a typical streaming output, you're gonna have a hard time seeing that. You guys show me, at the moment I turn off that ramping and make it too much, there is actually pixelation that we don't actually want to see. And that's why we have this stepping thing to make it smooth so that the stepping it looks like a pixel even though it's not. And that's the plateau, that's the overall, the screen distort function. That's the one that gives it both the pixelization and the curvature. And I did it in one because it's just easier to have one thing that does both of them because they have the same inputs. As outputs, there's 2 bits to the outputs. You notice there was the alpha function and the line height. Now, why do we need the alpha function? Because this looks round, it produces a round output. But if we simply take off the alpha function, you'll see what happens is that it fades to black. And maybe this is okay if you're overlaying graphics. But for me, I had the issue that because my graphics are all rounded and stuff, it creates these corners. It was easier for me to emit the alpha of the circle as well, so it clips to that. So this will actually, right now it's not clipping. If I put the alpha back on, it actually clips to the circle. And that makes it just easier to deal with in a game that has rounded graphics. Let me just have to save this again. And so the square circles go away there, or the bits of the circle go away. The other thing it emits is the scan line height. And if you see there's the line height as offset.y, this is the pixelated scan height. And it's feeding it into this other function called the scan line. Now we could take the scan lines off, but can I take the scan lines off, or can I just take I think I have to take the whole thing off. So if I remove it all, the whole scan line and barrel shape goes away. I don't have an easy way to just disable just the scan lines. Or maybe I could, maybe I can. Let's see, no, I think it's, how do I disable just the scan line? Color out, blurb out. What if I say the line height is exactly, actually let's be curious. What happens if I just say line height is 1? Oh, bad things happen, okay. Offset.y. All right, because these are all sub pixel values. So let's see, off 0.1 would be better. And now the line height is just really big. You just don't really even see it because this offset value is probably really, really small normally. Offset.y is going to be really, it's going to be a pixel 1. Let's put 0.1 on, see what happens. All right, I think the issue is that it has to line up exactly with the pixels, otherwise weird things happen. Okay, in any case, that was the line height. But let's say if I do divided by 2, that might give me something better. Well, what you have, and again, I think I've over-optimized this for modifications. That if you change too much, there's too many values that are dependent on it. But you can see what happens is it actually creates weird pixelization effects because the scan line is off. It's not mapped to the correct scan lines. So let's put this back to 1 and I'll just explain what that's doing then. This is doing the exact same thing that the virtual pixels is doing. This is doing the same thing, the scanline function. If we look at the scanline function, scanline float. It has a similar type of setup to the plateau function. And what it's doing is it's doing a gradient between the 2 values. And what if I just set it O equals Y? Okay, so this is the one without the anti-aliasing. This is actually a good example to see why you need the anti-aliasing, because this is the scan line basically without the anti-aliasing, and it just doesn't look good. It's pixelated, and it sounds really stupid that these are pixel graphics, but you don't want them pixelated because that's not the virtual CRT tube. So that's what this scan line is doing, is it's adding sort of anti-aliasly pixeled scan lines. I know that sounds really stupid. It's just a relatively simple function. It's the same one as the plateau function with slightly different values. And again, it creates this effect you've seen in other pixel games that have low res but high screen resolution support. You'll get like the well anti-aliased virtual pixels on the display. And that's what that's doing. That's what the screen distort function is doing. And that's how those work together. You'll see the screen distortion goes right into the sampling because the sampling samples from that screen distortion from the pixels. And that's how I sample clean pixels, is from that distortion. And there's a bit here. It's when working with these things, there's a bit of a nuance in Unity. These are going to end up in sprite aliases, sprite maps. Sorry, yeah, atlases. Sorry, atlases are sprite atlases. And so the UV gets all screwed up if you're in a sprite atlas. So everything here has to be UV adjusted within the sprite atlas. And this took a long time to get working. It's because it's really annoying, and I don't feel provides the right nodes to do this correctly. It has this local UV, but then I have to do all this mapping, like this weird mapping here that creates this partial gradient to get it offset halfway. I don't know why it's halfway off. And the other functions, I have hard-coded some adjustments to make that work. Just say it's frustrating. So if you do this on your own, you're going to get this all working. It's going to work great. And then you're going to start the game, and you're going to be partially sampling graphics because they're in an atlas. If that's the case, you come back to your shader graph and look, do you have something called a local UV in UV0 output? If you don't, then chances are you're not correctly supporting the atlas. It doesn't matter that Unity said the atlases are transparent. They are not. They actually affect the sampling thing. And then you're going to have to add an offset because it's just in the wrong position. So that's what this does. It's just some technical stuff. All of this stuff in the middle here is effectively just getting Unity to sample the pixel I want from the atlas. Whereas the other stuff is all the actual custom effect. Okay, and this center offset function, this is the one that's doing the actual gradient. Now I remember this gradient function. So that's why turning this off, you still have the gradient, because the actual shading gradient actually does follow the true spherical shape to some degree. So it doesn't matter that the scan lines don't follow the shape. The shading, this blackness, is actually following this. And this is just a center offset function. I don't remember what it looks like, but I'm guessing it's one of the simplest functions we have. I don't know what. Wait, I'm guessing it's one of the simplest functions we have, and yes, it is. It's simply calculating a distance from the middle. And it's based in UV coordinates, which is UV from 0 to 1, so since it's normalized, so you don't have to worry about this here, it's just renormalizing the coordinates. If we want to change this, you can get a different display, and you see it just shading it a different way. And is this correct value? I don't know. Correct based on one. This is pseudospace. So if I put it too high, you don't get that shading. So I'm pretty sure I came up with this value not from some physics calculation, but just from going up and down until I got one that visually looked reasonable for this display. And that's where this last part of the shader graph pulls together. We have the part that does the texturing based on the distortion. So the distortion is fed into the texturing and into the scanline generation. The UV is fed into the noise generation as well, and then it has the time-based effect, and then it takes a sampling texture and blends it with the noise. It's a blend function. It's a multiply blend function. And then it feeds it into two things. The texture, the UVs is fed into this circle to get the offset, and then it's multiplied by the texture here to produce the shaded thing, and then it's combined. It's doing a lerp here, which is really weird, but it's okay. It's doing a lerp here between the scan lines and the display. And the lerp here, instead of the multiply, ensures that it just gets the right scanline effect to get the effect. And then it just all pulled together, and the alpha is pulled directly from the scanline, so it keeps that rounding. It probably could have also come from the center offset, because the center offset also has the same alpha. And I don't know, actually, I'm really curious. Okay, it's similar alpha. You can see it's still rounded, but it's fading on the edges, so it's not exactly the same alpha. Right, so those are the parts of it. Those are the parts of the graphics in the game. That's for these little graphics here. This one should run too with little animations. I'll just show you that quickly, that they're actually animated. This one's just running the sample animation in a loop. And these, you can see, they're really low frame rate animations, but this blends into the effect of the game that this is a sort of steampunk monitor. Like if I was in steampunk age, I'd have this little monitor, and this would be really high tech for that. You have this pixelated display. And these graphics are 32 by 32 pixel graphics. The source graphics rendered as you saw in anti-alias pixels on the screen at 4 frames per second with noise that's run at 10 frames per second. And they just have various loops. All right, thank you very much for watching. If you like this video and want to learn more about Rabanaz, just come join the Discord channel where you can ask a lot of technical questions. Discord's probably the best for technical questions. If you have questions about the game, you can also ask there. We have Steam forums. You can follow one of the social media channels. Please wishlist the game on Steam. I'm positive you'll enjoy the game. And then you can see these ravens and all the other little raven characters in the game and see how we pull it all together. And also join this channel to watch other videos. I'll show more technical things from the game, from the other animations, from the way the event system works, and everything about Rabanaz from the technical viewpoint. Okay, thank you very much.